welcome to Biomaterials. What are we going to talk about today? Well, we're going to talk about a few topics. The first topic we're going to talk about is how to quantify molecular weight when you have a mixture of molecules. Then we're going to talk about two main classes of polymers. We're going to talk about thermoplastics and thermosets and thermoplastics. So thermoplastics and thermosets. And we'll talk about, what are distinguishing characteristics between the two. What are applications where you might want to use thermosets versus thermoplastics. What are sort of some distinguishing characteristics. So, if you were to choose, want to choose a polymer for one, for some engineering application, you might be informed as to which one you want to choose. Then we're gonna take a deeper dive into the microstructure of these two things. So in particular, we're going to look at the microstructure of thermoplastics. So microstructure of thermoplastics. And in particular, there are two main types of microstructures that we see in thermoplastics. An amorphous microstructure. So an amorphous microstructure versus a semi-crystalline microstructure. Then we're going to say, okay, basically these are the two microstructures that exist. We're then going to make connections between temperature, mechanical properties, and in particular the stiffness or Young's modulus, and the microstructure. So basically, what is the connection between temperature and microstructure? What is the connection between microstructure and stiffness? What is the connection between temperature and stiffness? We'll sort of discuss all of these together in the context of amorphous versus semi-crystalline thermoplastics, and then we'll also sort of make a connection between some of these things and thermosets as well. And some terminology that we'll use in describing this relationship right here is a so-called glass transition temperature. Or I guess the glass transition and the temperature associated with it. So glass transition and glass transition temperature. We'll also talk about a process of sort of softening and viscous flow. And then we'll also talk about something that is sort of distinct from softening and viscous flow and exists actually really only for semi-crystalline polymers, which is called the melting temp. And actually, that's not really, we'll talk about it in detail later. It's not really the polymer becoming a liquid, but it's rather an appreciable change to its microstructure when it still remains solid-like. And we'll also talk about the rubbery plateau. For polymers. And then I'll very briefly at the end describe sort of a shortcut which can sort of give us some rough predictions of when these sort of microstructure and mechanical property changes might be occurring in terms of temperature. So basically a shortcut to help get a rough picture of the connection between temperature and some of these microstructure things is a technique called differential scanning calorimetry. Which is basically a technique that, with a relatively straightforward experiment in lab, you can get the connection between temperature and some of these properties. So that's where we're headed. Let's now start talking about how we might quantify molecular weight. So first, take a moment now and think, why might it be important to quantify molecular weight with polymers? So why important to have precise quantitative definitions? Why do we even care that much about molecular weight at all? Well, the reason we care about molecular weight is, if you remember, molecular weight, when we imagine these polymer chains packing together, the smaller the molecular weight, the more frequently we had ends of molecules, and the more frequently molecules ended, the less able they were to pack against one another, and we ended up with lots of dead space. And what did that mean? That basically lowered chain-chain bonding, which basically lowered mechanical properties. So if molecular weight is this important in terms of determining something's mechanical properties, it might be nice if we had sort of quantitative relationships, right? Like, wouldn't it be nice if we had a quantitative relationship between molecular weight and modulus of elasticity, or molecular weight and yield strength, or molecular weight and a melting temperature? Right? Wouldn't it be nice if we had quantitative relationships between all of these things? And well, if you want a quantitative relationship between all of these things, you're going to need a quantitative way to define a molecular weight. And of course, molecular weight is pretty straightforward for pure substances. For example, H2O, where every water molecule is the same as every other water molecule. Of course, if you neglect things like deuterium or heavy hydrogen or different isotopes or things like that, if we sort of ignore that, every water molecule is the same as every other water molecule, right? So they're all the same. So the way you basically calculate the molecular weight of H2O is essentially 2 times the molecular weight of hydrogen plus 1 times the molecular weight of oxygen, right? So we do that, right? 1 mole of H2O has 2 moles of hydrogen, 1 mole of oxygens. So you add up all of those grams per mole, and you put them all together, right? So if you remember the units. The units we typically use for molecular weight would be grams per mole. And of course, the molecular weight, regardless of whether it's just of hydrogen or of H2O, we're talking about units of this. But for polymers, this calculation isn't all straightforward, because oftentimes we have a distribution of chain lengths. So, for example, you might have some kind of plot here where we basically have like a number of chains in your sample, and the molecular weight of each chain and what you might end up with is essentially some kind of histogram, right? Where you have, very, very few short chains, you have very, very few long chains. Most chains are sort of, around some particular value, but there's sort of a distribution, right? Not all chains are the same length, right? We have some short chains, right? We have, a few number of short chains, a few number of long chains. Most of our chains are close to this average, but, exactly how do we define that average? So we have a few short chains. We have a few long chains. And, basically most are close to the average. But how do we even define an average anyway? Right, so what we're going to talk about today is basically two different ways to define an average molecular weight. So there are basically two ways to define an average. And you might be like, hey, Landon, like, way I grew up, we only had one way to define an average. And basically, there are two different ways to define an average, depending on sort of how you weight, how you sort of weight chains of each length. So what does this mean? How do we actually sort of put equations to these things here? So basically, the two ways to define an average are M sub n, and M sub w. And M sub n is called the number average molecular weight. And M sub w is what we would typically call the weight averaged molecular weight. So we have a number average molecular weight and a weight average molecular weight. And if I were to sort of think about each of these definitions, roughly qualitatively, what M sub n is the total mass of everything in your sample. I guess it's the total mass of everything in the sample. Divided by the total number of molecules in the sample. Right, so if I have X grams, if I have X grams of polymer and Y number of molecules, right? If I were to somehow able to look into a polymer and say, okay, 1 molecule, 2 molecule, 3 molecule, 4 molecule, etc. Right? I guess it's total number of molecules. I guess it's total number of moles, more strictly speaking, right? If I were to able, say, okay, there's two moles of molecules in this sample, and there's 18 grams of polymer in this sample. I just take the number of grams, total number of grams, divided by the total number of moles, and move on with our lives. The weight averaged molecular weight is basically I sort of give extra weighting. So it's a weighted sum of the mass of each type of the total mass of each type of molecule. So it's a weighted sum of mass of each molecule type divided by the total mass of the sample of everything in sample. And I'll bust out some equations to sort of further these two definitions right here. So we have these two ways to define molecular weight. Let's define some variables. So one variable that I'm going to define is called M sub I. And that's the molecular weight of one chain of species I. Species or length I. So what might I mean by that? Well, let's say I had, let's imagine that my polymers are these blocks right here. If one repeat unit, like this, this, let's say one block right here equals, let's say 10 grams per mole. So I might say, M1 is equal to 10 grams per mole. If I were to, for example, have two, like this would be like a monomer. If I had a dimer with two blocks locked together, I might call this, this one M2, where I essentially have two blocks bonded together. So I might call M2, I might call this 20 grams per mole. All right, and then you could imagine if I had, a block like this, M4 would be like 40 grams per mole. So it's basically like, if I had a mole of chains of all of this particular length, 1, 2, or 4, or whatever, how many grams per mole would that sort of pure sample of that chain length be? So that's basically what M sub I is. So another variable that we're going to use in these equations is N sub I. And that's basically within our sample, how many moles of chains of chain length I do we have. So for example, if I had a sample that let's say looked like this, I would say N sub 1 is equal to 3. If I guess if each of these sort of represents a whole mole of molecules, N sub 1, right? If I'm looking for, how many things in this sample have a chain length of 1, 1, 2, 3, chain length of 1. And I guess it would be, we'd saying each one of these represents a mole. N sub 2, how many chains do I have of length 2? Well, actually just 1, right? So N sub 2 would basically be equal to 1 mole. I essentially have 1 mole of chain length 2. And how many moles of chain length 3 do I have? I have 3 moles of chain length 3 in this sample here, right? So it's basically, how much of the small ones do I have? How much of the large ones do I have here? So in a sense, what I plotted on the y-axis right here, if you imagine this is sort of like a histogram for distributions of chain lengths, this is N sub I for this particular sample. And if you imagine what I'm putting on the x-axis right here is M sub I. So, when M sub I is small, I'm talking about just a few short chains down here. There are just a few long chains, all bonded together. And there are lots of medium length chains, right? So there's like a whole bunch of there's lots of medium length chains, right? So medium length means an M sub I somewhere in the middle here. This is low M sub I, this is high M sub I, and N sub I is basically how abundant. So this is abundance, this is chain size. So M sub I is how how big each chain can be in terms of its grams per mole. N sub I is how abundant each type of chain is. So that's the two definitions, or those are some intermediate definitions that are useful in our overall definitions. So M sub n Well, m sub n is if I were to sum up m sub I times n sub I. So basically, like, you know, how many length 1s do I have? How heavy is each length 1? M sub I times n sub I is basically how much, you know, how much is the total mass of everything in the sample that's 1, right? So, you know, basically, if I were to look at this right here, and basically say, all right, you know, what's the total mass? What's the total mass of this? That is like the total mass of everything of length 1. You know, or I guess if we wanted to generalize it, you know, here it's of length 1, or in general, or I in general. And then you can imagine if I marched through like I equals 1, and then I equals 2, and then I equals 3. When I did that, I would sort of get the total mass of everything in the sample, right? So if I summed all of that up, that would basically represent this sum right here. Like the total mass of everything that I've circled in red is basically the sum of all of these individuals kind of doing it length size by length size. And of course, we divide that by the total number of molecules, which is basically what I get when I just count 1, 2, 3, 4, 5, 6, 7, you know, something like that. So the total number of molecules is the sum of n sub I, right? So this is basically the total number of molecules in the sample. If you remember, m sub w is this sort of weight averaged thing. So basically what m sub w does is it gives extra weight to the longer molecules. So m sub w is equal to the sum of m sub I squared n sub I divided by m sub I times n sub I. So if you remember like the total mass of everything in the sample, you know, that's the denominator in m sub w and the numerator in m sub n, right? If you remember, total mass of everything in the sample is the denominator for m sub n. It's the total mass of everything in the sample is the numerator for m sub n, and it's the denominator for m sub w, right? So that's why these look the same. But there's this sort of extra factor of m sub I in the numerator within the sum of the numerator for n sub w, and basically, you know, this sort of kind of squared business right here, this definition of molecular weight sort of emphasizes the impact of longer chains. And you might say, like, geez, Lannon, like, why do we need two separate definitions of molecular weight? And if we go back to our motivations here, you know, there's this connection between like molecular weight and dead space. It turns out that some macroscopic properties correlate better with m sub n, and other macroscopic properties correlate better with m sub w. So if you're trying to, you know, have some sort of quantitative prediction of melting temp or stiffness or yield strength or density or whatever, some of those predictions correlate better with m sub n, some of them correlate better with m sub w. So why two definitions? Why two definitions? Some correlate better with m sub n, so some macro properties for example, stiffness or yield strength, etc., correlate better with m sub n, others with m sub w. So we need two definitions to basically plug into formulas that people have derived experimentally to figure out these correlations. So let's now do a pause and ponder question. Imagine I had the following set of imagine I had the following set of molecules. So pause and ponder. Imagine I had the following set of molecules. Let's say I had three molecules of length 1. Let's say I had 2 molecules of length 2. Let's say I had 3 molecules of length 3. And just 1 molecule of length 4. Right, so I had three singlets, 2 doublets, 3 triplets, and 1 quad. Take a moment now, pause and ponder. What would M sub n and M sub w be for this polymer mixture? It's a little hard to see everything on the screen here, and it's a little messy, so I'll sort of tidy it up. So I have 3 singlets, 2 doublets, 3 triplets, and 1 quad. And given a single repeat unit, weighs 10 grams per mole, and each sort of picture drawn here represents a whole mole of that type. So each picture represents a whole mole. So I have 3 moles of this type, 2 moles of this type, 3 moles of this type, and 1 mole of this type. So pause and ponder. Use your definitions of M sub I and N sub I, and do this. Well, if you're looking for a little guidance, what I like to do is maybe help kind of calculate things in sort of chart form. So to sort of organize my information and compute these things here, if we had a ton of these, we might sort of do it with a spreadsheet. But let's break down this pause and ponder just a little bit if you're getting kind of stuck, and make a column with N sub I, M sub I, N sub I times M sub I, and N sub I times N sub I, M sub I squared, N sub I times M sub I squared, right, where it's just the M sub I is squared. Let's take a moment now, try to complete this. Well, N sub I, right, I have 3 moles of this type, so I'm going to do 3. I have 2 moles of this type, 1 mole of this, or 2 moles. I have 3 moles of the triplets, and I have just 1 mole of the quads. M sub I is the molecular weight of, if I just looked at one of these chains, or one of these chains, or one of these chains, or one of these chains, what's the molecular weight of that, of just a single chain? Right, that's the molecular weight of a single chain. We know the repeat unit is 10 grams per mole, so each of these ones have just 1 repeat unit, so that's 10 grams per mole. A single molecule of chain length 2 has 2 repeat units, so that means it's 20 grams per mole. A single chain of the triplet would be 30 grams per mole, right? Just a single chain of the triplets, 30 grams per mole, and a single chain of the quad would be 40 grams per mole. N sub I times M sub I, what's that? Well, that's just the product of these first two columns. So all of the mass of everything here, is 30. All of the mass of everything here is, this times this, so that's 40. All of the mass of everything here is 3 times 30, so that's 90. And all of the mass of everything here is 1 times 40, or 40. So that's that. N sub I times M sub I squared. I guess I could just multiply these two columns, times together. I already did N sub I times M sub I, so I could just multiply it by M sub I again to get 300, 800, 2700, and 1600. And if we just want to, make sure all of our units, right? This would be in moles. This would be in grams per mole. This would be in grams, right? And this would be in terms of grams squared per mole. Not really very physically intuitive units here, but again, these are what we use in our definitions, so that's what we got to do. Now, if you remember, M sub n and M sub w are basically have sums of each of these quantities here. So the sum of n sub I is basically what I get when I add everything together in this column, right? So if I basically take this column and add it up, if I add up all of the n sub i's, this is like the total number of molecules. So it's like 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Or 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 9 right here. This is the sum of n sub I is equal to 9, right? That's if I sum up this column, that's that. Summing up m sub I is of no use. Like don't bother summing up this column. It's basically would be nonsense. But summing up n sub I times m sub I is useful in this here, right? So if I sum up n sub I times m sub I, that's what I get when I total this column right here. So if you do that, you end up with 200. Oh, I should get my units here, right? This would be 9 moles. This would be 200 grams. And then if I sum up n sub I, m sub I squared, that's going to be useful in my m sub w right here. So sum of n sub I, m sub I squared is basically what I get when I add up all of this column right here. I think it's 5,400, and it would be grams squared per mole. So then it's pretty straightforward to calculate m sub I and n sub I from these right here. So I think you end up with mn is equal to this divided by this. So you end up with 22.2 grams per mole, right? If we have grams divided by moles, right, the units work out. And then m sub w is what we get when we divide this by this. So that's 5,400 divided by 200, or 27 grams per mole, right? And if I take grams squared per mole divided by grams, then I end up with grams per mole. So the units work out there too. So you notice, basically, depending on which definition you use, you might get a different average, and basically that average is do you more heavily weight the big molecules? Because a lot of times it's really the large molecules that dominate the structure and function and properties of these things. It's really the big ones that sort of carry all the weight, no pun intended. Here, or is it sort of a more like just total mass divided by total molecules that really makes more of a difference. So different applications, different formulas, different correlations, work better with each of these things right here. One last definition that I'm just going to sort of throw in at the end is the Polydispersity Index. And that's basically a measure of how homogeneous is our distribution of molecules. And basically, a polydispersity index of 1 means it's totally homogeneous. And if it differs from 1, then you have a dispersed population, right? So a totally homogeneous, if we did this calculation for water, the polydispersity index of water, would just be 1, since every H2O molecule is the same as all the others. But for something like this, we would get a different definition, and some people call polydispersity index PDI, some people call it D, whatever. I like PDI since it sort of more clearly brings into the definition here. And anyway, polydispersity index is essentially defined. It's defined as m sub w over m sub n. So basically, calculating m sub w, calculating m sub n. Their ratio is the polydispersity index, and the more these two differ from one another, the more sort of non-homogeneous this distribution is. And polydispersity index can sort of also have influence on some of these mechanical properties. Basically, some of these properties here depend not only on m sub n or m sub w, but sort of also depend on how dispersed the distribution is. So sometimes calculating PDI is helpful in that application too. All right. So thus concludes our discussion. On how we'd like to quantify molecular weight. Now let's move on to talking about two general classes of plastics, thermosets and thermoplastics. So let's make a chart. Let me move some of these thermoplastics out of the way. Legos are made of ABS, which I think is a thermoplastic. Anyway, thermosets and thermoplastics. Let's make a chart. And we'll put thermoplastics on the left and thermosets on the right. And first, I'll talk about what the microstructure would look like, or I guess even the nanostructure would look like if I were to sort of zoom in all the way to the molecular scale. What does a thermoplastic look like? What does a thermoset look like? So thermoplastics, if you imagine what thermoplastics are, they're just these long chains They're just long chains, and the strength basically comes from, if I have adjacent chains, right? If I have some adjacent chain, then I get some of these chain-chain interactions that I was talking about in a previous lecture. So when I have a big long chain, I get numerous but weak chain-chain interactions. thermosets are different in that there's sort of two possible states in a sense that a thermoset can be in, or two sort of situations. One situation is before curing or before cross-linking. Before curing, or maybe before or cross-linking. And after cross-linking. And you basically have two different situations. So before curing, what you do is you have basically a bunch of short chains of polymers. So each of these chains, they're covalently bound within one another, but they're nowhere near as long as the chains of thermoplastics. And basically, because they're short, this basically is it's like a gooey liquid. So this flows easily. And after cross-linking, there's basically some mechanism by which you could take what used to be a bunch of sort of separate chains, and you build covalent crosslinks between one another. So you might, or I'll do the crosslinks in a different color. So basically, you build these crosslinks. And then you can imagine, if now everything, each of these small chains are now sort of covalently cross-linked to one another, then covalent crosslinks give this material its strength, right? So it flows easily when nothing's cross-linked to one another, but then after cross-linking, the covalent crosslinks, I'll abbreviate crosslinks as X-links here. Covalent crosslinks give strength. And, basically after cross-linking, it becomes a solid. So, how does this cross-linking happen? Well, a lot of times you don't just have these small chains, but you also have some monomers. So monomers of things that can form these cross-linked bridges. So monomers that can bond and can bond once activated. And then also in this mix as well, you might have some sort of what we'll call initiator molecules. So these initiators that basically starts the cross-linking process. So basically the initiators can sort of react with these chains or with these monomers, and they sort of start the process of these bridges forming. So initiators sort of start the process of cross-linking. Now, why is this called a thermoset? Well, this idea of setting is basically these initiators activate the monomers then cross-link here. So this set is basically this cross-linking process here. So once a thermoset is set, it's locked in place right here. And these initiators start the process, and they're activated by heat or light, or some other, maybe some chemical present. So basically these, and the very first types of thermosets, we're sort of set by heat. So basically the heat starts the initiator, and that's why they're called thermoset, is because heat started the setting process. In contrast, for thermoplastics, the way we sort of form a shape, you can imagine this thermoset process. You basically pour something like this into a mold, and then heat it up or shine light on it or something like that, and then it will sort of cure in that shape, right? It'll, once it's set in that shape, it's locked. Thermoplastics, you basically heat it to break these bonds, and then cool it down to sort of reform these numerous weak chain interactions. So let's sort of kind of outline characteristics of each of these here. Thermoplastics basically soften and flow once heated up. And they sort of regain some stiffness and strength once they cool down. They soften, and the idea here is basically because these weak chain interactions can sort of be broken and then reformed and broken and then reformed, this process of softening and flowing, this process here can be repeated. And that's nice. For example, this process of basically softening and then reforming their structure, this has certain applications. For example, FDM 3D printing. You basically buy a spool of some thermoplastic. That spool then goes through a heated printer head, comes out, very soft and kind of liquidy, and then once the printer head sort of, extrudes out that little bead of material, that thermoplastic then cools down and solidifies next to its neighbors. So, this process of softening and repeating, 3D printed plastics are, for FDM anyway, are made this way. So FDM 3D printing is basically a way to do this. Recyclable plastics. Basically, a plastic must be thermoplastic in order for it to be recyclable. So, when you throw away your plastic waste in the recycling bin, an embarrassingly small percentage of it, but some percentage of it actually ends up getting recycled. Most of it goes to a landfill, unfortunately, but some small fraction of that plastic goes to the recycling plant, where they basically grind it up, melt it down, and recast those thermoplastics into new things here. We contrast this to thermosets, where basically the covalent bonds, the covalent crosslinks, are permanent. So what does this mean? That basically means that they're typically stronger, and they're typically stiffer and stronger than thermoplastics. So basically stiffer, and stronger than thermoplastics. Right? These covalent bonds are super strong, but they basically they can't melt. Once these covalent bonds are formed, you can't sort of melt it and have these original chains flow past one another again. Like, once those covalent bonds are formed, they're done, baby. They're locked in. So what does that mean? They can't melt. They can't be recycled. And of course, this breaks my heart, right? So there are some types of 3D printing, for example, stereolithography, so SLA 3D printing. So SLA 3D printing typically uses thermosets, where basically a laser sort of scans across a bed of liquid, uncured thermoset, and the laser activates only the small regions of the liquid thermoset that you want to solidify. So basically, a laser scans and selectively cures. cures to form the shape. Or when you go to the dentist, if you get one of those like white colored fillings in your teeth, part of that filling material is made from a thermoset that's cured with light. So the dentist drills out your decayed tooth, fills in that decay with a mixture of thermoset and ceramic, and then shines the blue light on it to cure it in the proper shape. So in a similar way to 3D printing, also like some dental fillings can basically use this. But the key thing with thermosets is, like, once those crosslinks are formed, they're done. They can't be recycled. They're permanent. And often, so what does this mean? For temperature, for situations where you want a plastic to be able to withstand high temperatures, thermosets might be the best thing, right? If you want good temperature resistance, you might want to use a thermoset. Whereas if you want your material to be recyclable, you might choose a thermoplastic. So there are pros and cons, and depending on your application, whether you want it to be recyclable or you want it to be permanent, or what type of manufacturing technique you want to use, you might choose one versus the other. So that's the distinction between thermoplastics and thermosets. Let's now look at connections between temperature, stiffness, or maybe some other mechanical properties, and the microstructure of what's going on. And in particular, let's look at amorphous versus semicrystalline polymers. So first, within thermoplastics, which again are governed just by numerous but weak chain-chain interactions, there are basically two predominant microstructures. So again, if you had really good vision and could zoom way in to what's happening with plastics, there are amorphous microstructures and there are semi-crystalline microstructures. And if you were to zoom way in to the level of individual polymer chains, an amorphous microstructure would just sort of have a bunch of random coiling. Whereas a semicrystalline would have regions of regular structure, which are the so-called crystalline regions, but those regions would sort of be buffered between one another by amorphous regions. So semicrystalline means that here's the crystalline part, but it's only semicrystalline in the sense that these crystalline regions are buffered by amorphous regions. So we might have some amorphous stuff. So the key thing here is the crystalline, the crystalline part are like these regions right here. These regions right here that have a very regular structure with tight chain packing. So this basically has a regular structure and tight chain packing. And the amorphous structure basically is just a whole bunch of randomly packed, randomly coiled packed things here. So with this tight chain packing, we can get sort of numerous and strong, or I guess numerous and relatively strong chain interactions, right? So we get lots of chain interactions. And here, you know, we still have some. So we have only some chain interactions. Basically because, you know, they're all packed together randomly, you know, they only sort of bump into one another or sort of become close enough to one another to have some interaction occasionally. So that's basically the two microstructures here. So you might imagine, you know, like what might make something amorphous versus semi-crystalline. You know, which one is which depends on chemistry and temperature. On chemistry and temperature. So if you remember to a previous lecture, I talked about like isotactic versus atactic polystyrene, or isotactic versus atactic PVC or polypropylene. For example, an atactic polymer, remember, like isotactic was basically like, you know, all of the side groups point up, and so atactic, remember, was basically you know, side groups pointing in random directions, up or down out of the plane. So side groups are random, up versus down. You know, so if something is atactic, then the chains can't pack in to these crystals as very nicely, so it's more likely to have an amorphous structure. An amorphous structure. And for example, iso or syndiotactic, this is more likely to be semicrystalline. Where basically if something is isotactic, you know, everything is up or everything is down, those adjacent chains can pack together quite nicely. Or syndiotactic, where half of them are up and half of them are down, those, you know, those chains can also zipper together with their neighbors very nicely and sort of pack into these semicrystalline structures. So that's basically the two structures here. You know, so take a moment now and think, you know, which one do you expect to have higher stiffness and strength? So pause and ponder. Which microstructure is more likely to have higher stiffness or yield strength? Again, we can't be sure, right? Because there are certainly some amorphous polymers that are stronger than some semi-crystalline ones, and some semi-crystalline ones that are stronger in amorphous. But the trend would be that semi-crystalline. The trend would be that semi-crystalline ones would tend to be stiffer and stronger than amorphous due to the more numerous chain interactions. Let's now talk about how what about temperature, right? How might temperature affect what about the effect of temperature? So let's take a look. So let's imagine we were to make a plot of modulus of elasticity, or Young's modulus, versus temperature. you know, what might you expect this curve in general to look like? So you know, sort of draw, you know, take a moment now and sketch, you know, what a general trend would be. Well, in general, you expect as you heat something up, you typically would soften it, right? You would soften it or make it more compliant or something like that, right? So, you know, the typical trend would be at low temperatures, we expect things to be very stiff, and at high temperatures, we expect things to be very compliant. But it turns out that if we want to look a little bit more deeply between temperature, stiffness, and microstructure, spoiler alert, it's going to be a little bit different for amorphous versus semi-crystalline polymers, and it's not quite so straightforward as just like a line that goes down like this. So first, what we need to do is we need to consider, amorphous and semi-crystalline polymers separately. So first, let's talk about amorphous. So amorphous polymer. So what it turns out is at very low temperatures, we expect to have a very high stiffness. But that stiffness is actually pretty constant for a while. And then what happens is that stiffness goes down and then kind of plateaus again for a little bit, and then sort of just continues to kind of go down and down and down and down above, you know, once we get warmer than some temperature here. And, you know, anytime you sort of notice something drastic happening at a particular temperature, you might look into, you know, what's going on here. So what goes on here is what we typically call the glass transition temperature. So this is given a special name, T sub G, and T sub G is what we call the glass transition temperature. And basically what happens at the glass transition temperature, you can sort of imagine, you know, what happens here versus what happens here. Here is what's called the glassy state. And here is what's called the rubbery plateau. And if a polymer is in the glassy state, so, you know, let's look at this amorphous polymer right here, right? Let's imagine that instead of my headphones, these are polymer chains right here. When something is in the glassy state, carbon-carbon bonds lack, right? If you remember, these polymers are typically made of a carbon-carbon backbone. Carbon-carbon bonds lack sufficient thermal energy to rotate. Every carbon in the chain essentially rotates and rotates and rotates, and that's basically what allows polymers to be bendy. So basically, carbon-carbon bonds, but below the glass transition temperature, when you're in the glassy state, is carbon-carbon bonds can't rotate. So to sort of draw an analogy here, you know, I could have this sort of amorphous microstructure right here, but if none of these chains can really like twist or deform to slide past one another, everything is sort of totally locked together. And if I try to stretch this microstructure, basically none of these chains can sort of rotate to wiggle themselves out of the way of one another. So it's basically like if I took these headphones and sprayed a bunch of hairspray on it or sprayed a bunch of glue on it to basically lock it all into the structure. So carbon-carbon bonds can't rotate, and the chains are basically locked together due to low thermal energy. So chains locked due to low thermal energy. Once I'm in the rubbery plateau, which is actually what the plastic that makes up the coverings for these wires are, then the carbon-carbon bonds can rotate. And basically what this means is basically it's still a solid, but chains can uncoil. So it's still a solid, but chains can uncoil. So if you were to, instead of plotting modulus of elasticity versus temperature, if we were to sort of look at a polymer in the glassy state versus a polymer in the rubbery plateau, plot what you think might be a stress strain curve for something in the glassy state and also something in the rubbery plateau. So take a moment now, pause and ponder what you think those stress strain curves might look like. Well, in the glassy state, high stiffness, right? So we anticipate the slope being very high. But if these chains are all locked together, once I start pulling these chains apart, they're just going to snap rather than be able to slide past one another. So basically, if the chains snap rather than sliding past one another, I have almost no ductility. So I have a very high stiffness, very high slope here, but almost no ductility. When I'm in the rubbery plateau, that's like a rubber band here. I can stretch out that rubber band an immense amount because all of the chains in this rubber can freely slide past one another. So if I'm in the rubbery plateau, I have much less stiffness, but I can go much, much, much farther. I can have much, much, much more strain. And this might even be way, way, way more out here, like it's out here. So some time ago, there was a disaster in the Lannon household. I had made a bunch of pesto, and I was like, oh, I'm going to freeze the pesto because I want to, enjoy it all throughout the winter. So I took a whole bunch of leftover containers made of polypropylene, recycling number 5, polypropylene. Froze my pesto in here, but it turns out that polypropylene's glass transition temperature is somewhere pretty close to the temperature of my deep freezer. So basically, I put a bunch of pesto in these containers. I took one out of the freezer and dropped it, and the container just shattered. The plastic was super, super rigid. And basically that means, this plastic below the glass transition temperature, led to a tragedy in the Lannon household where I'd spent all of this time making this delicious homemade pesto, only to have the container just smash into a million pieces when I dropped it on the floor next to my freezer. So much sadness, right? Basically, the material was stronger, but it lost all of its ductility, and that loss of ductility, was problematic for the application of, surviving a sudden drop on the floor. So here's the glassy state, here's the rubbery plateau. So around freezer temps, polypropylene transitions from something pretty compliant, but also pretty ductile, to something less compliant and much more brittle. And of course that has implications. If I were to take this polypropylene and heat it up even more, then it basically becomes, it essentially becomes a liquid. And basically, sort of flows as a viscous. It basically sort of undergoes viscous flow. So, the way they manufactured this polypropylene container was they basically had a mold or something like that, and heated up the polypropylene so much that it essentially became a viscous liquid with almost no stiffness, floated into this mold and let it cool down until it was, sort of somewhere around here, then popped it out of the mold, and, now we can use it to store our leftovers. So, this is, for example, how they molded it. Basically, they heated it up past sort of this sort of roll-off temperature right here. I hesitate to use the term melting right here because melting actually means something very specific in the context of semi-crystalline polymers. So now let's look at this at a plot of stiffness versus temperature, but instead of for amorphous polymers, which I've drawn right here, let's do it for semi-crystalline. So let's look at stiffness versus temperature, and now let's do it. I'll do it in a different color for a semi-crystalline. So for a semi-crystalline polymer. So for a semi-crystalline polymer, we still have this glassy state right here, and it turns out we only get a little bit of a dip in terms of the stiffness at the glass transition temperature. And then later on, only later on, do we get a much more pronounced dip in terms of a loss of mechanical properties. So so we still have our T sub G right here, but then we have this other sort of roll off right here, which I'll call T sub M, and this is what we call the melt temperature. So what's the key thing with a semicrystalline polymer? In this state, we have our crystalline regions, and we also have our amorphous regions. And below the glass transition temperature, both the amorphous regions and the semicrystalline regions are rigid. So both rigid, right? In the same way that an amorphous polymer below its glass transition state is also rigid. Between Tg and Tm, we still have our crystalline domains, and we still have amorphous domains. Basically, the crystalline region is still rigid. So the crystalline region is rigid, but the amorphous region is compliant. So we get a little bit of a dip. We get a little bit of a dip in the mechanical properties right here. And then, below the melting, what's called the melting temperature, is basically the crystals unpack. Basically, there's finally enough thermal energy where the molecules, rather than forming that nice tight sort of zipper-like structure between adjacent chains, the molecules have so much thermal energy that they can no longer pack tightly into crystals, and it basically becomes totally amorphous. It becomes totally amorphous, and basically, with that, it has a severe loss of all of its mechanical properties. So this is basically, so if you were to look at a stiffness versus temperature curve, basically by how extensive this drop in mechanical properties is at the glass transition temperature can inform you, about whether basically all of the material becomes compliant, or just a little bit of the material between the crystalline regions becomes compliant above this particular temperature right here. If you were to take an amorphous polymer and cross-link it, it turns out you don't observe this phenomenon right here, and essentially a cross-linked thermoplastic, in a sense, would be kind of like a thermoset, right? If we took a thermoplastic and heavily cross-linked it, it would behave similarly to a thermoset. So basically, if you cross-link a thermoplastic, we don't really sort of observe this viscous flowing melting temperature, basically because the polymer chains can't totally slide past one another because they're still covalently bound. So basically, it turns out that you don't get this loss of mechanical properties even when you heat it up a lot, and basically the material itself just sort of thermally decomposes into individual atoms before it really even melts. So there's cross-linked thermoplastics and thermosets. There's no such thing as really melting them. It just, we just sort of get this thing over here until the temperature is so high that it just, pyrolyzes or scorches or something like that. So that's the relationship. That's the relationship between all of these things right here. Let's now take a look at this tool that we can use called differential scanning calorimetry to essentially measure these sort of changes that we observe. So differential scanning calorimetry is basically a shortcut to finding like Tg, Tm, etc. These sort of important characteristic temperatures. So if you imagine the people who generated these graphs, like this was a pretty tough experiment to run. You basically needed to create a whole bunch of samples of your plastic. You needed a materials testing machine to get a stress strain curve. You then needed to extract the slope from that stress strain curve, and you needed to do it at a whole bunch of different temperatures. So not only did you need a fancy materials testing machine, but you also needed to take that fancy materials testing machine and put it in a temperature controlled environment. Oof, yikes, right? That's a non-trivial amount of work to do for that right here. And you can imagine, if you're like tinkering around with different recipes for plastics or polymers, all that stuff here, it would be nice if you had a way to just know when some of these important temperatures, are going to occur. So it turns out differential scanning calorimetry won't give you all of the information of this plot right here, but it's a shortcut to finding these important temperatures, the TG and the TM and stuff like that. So what do you do in differential scanning calorimetry? You basically have two heaters. So we have two sort of pans with electrical heaters. And into one of those pans, you place a polymer sample. And in the other one, it's empty. And the differential part of differential scanning calorimetry, so the differential part, is we measure the difference in the energy, in the thermal energy going to each pan. So measure the difference in thermal energy. You measure the difference in thermal energy going to each pan, and you also have temperature sensors. Temperature sensors essentially measuring the temperature of the pan. And if we were to sort of imagine, if I took some water and I wanted to heat up that water, as I put more and more and more heat into that water, the temperature of the water would rise until the water reached its boiling point. And then once the water reached its boiling point, that temperature would sort of plateau as the energy went from converting the water from liquid to steam instead of raising the temperature of the water. So if you imagine if I have these electric heaters and I'm sending heat into the polymer sample and I'm also sending heat into the pan, I can take the difference to essentially account just for the heat that goes into the polymer sample. So that's the differential part. The scanning part is I'm continuously raising the temperatures of these two samples. And basically when I sort of notice what would be a temperature plateau, then, so temperature plateaus are basically sort of equivalent to phase changes. So I basically measure how much thermal energy is going in, and if temperature plateaus while still absorbing heat, then that means there's a phase change. In the same way that if I were heating up water, that water would be increasing temperature until I hit its boiling point, and then that temperature would sort of plateau at its boiling point until I had converted all of that water to steam. The same thing happens with polymers. Thermal energy goes to heating it up, thermal energy goes to heating it up, thermal energy heating it up. And then instead of that thermal energy going to heat it up, that thermal energy goes into giving the molecules enough energy to wiggle past one another. So there's a phase change at these plateaus where basically that thermal energy goes to reconfiguring microstructures instead of heating things up. So that that energy can either go into making these carbon-carbon bonds have enough energy to sort of unlock and rotate past one another, or that energy can sort of go into unpacking the crystals. All right, so the energy goes to freeing the carbon-carbon bonds to rotate, Or for semicrystalline, that energy goes into unpacking crystals. So in the same way, it takes a lot of thermal energy to unpack water molecules from ice crystals to make them liquid. It takes thermal energy to unpack polymer crystals to make them amorphous. And this is something that you can basically observe with a differential scanning calorimetry experiment. And so differential in the sense that you sort of have this control pan to measure only the heat that, just by taking the difference, you measure the heat that just goes to the polymer. Scanning in the sense that you are exploring a broad range of temperatures to look for phase changes, and you know that whatever phase changes this heat phenomenon happens are the same temperatures that these glass and sort of melting, glass and melting temperatures occur. And the calorimetry, calories are a measure of thermal energy, so that's basically this measure, this measurement right here. So thanks for watching. Hopefully you now have a clearer vision of how to quantify molecular weight when we have a mixture of polymers. And you also have some ideas between thermosets and thermoplastics and how the microstructure for the two differ from one another. And then within thermoplastics, how the microstructure differs for amorphous versus semi-crystalline things. And then you also have a clear vision of how temperature might change or alter the microstructures, and also how the microstructure and temperature influences the mechanical properties through these plots here. So in an engineering application, you aren't expecting something that has a stress-strain curve that looks like this, but ends up having something that looks like this, or vice versa, expecting something to be very stiff and strong when actually it ends up being really compliant. We certainly don't want to use something out of its specified temperature range because we could sort of suffer a loss in our desired mechanical properties. So and then we talked about differential scanning calorimetry, where a full characterization of this might be difficult, but we can at least get a shortcut to estimate the important temperatures with a pretty small and compact and fast benchtop experiment. So thanks for watching, and good luck with your study of biomaterials.